So if you remember, a couple of days back, I actually draw a graph like this. Uh, I tried to draw, to be honest, a graph like this, where I showed that the graph of the exponential function and the natural logarithmic function um, is actually a mirror image of each other. If you just have a mirror like this, creating a 45-degree angle with the x-axis, if you have a mirror like this, these two graphs will look like a mirror image of each other. In other words, in mathematics, we say it's symmetric. That means it behaves similarly. Okay. So there is a certain relationship between logarithmic and exponential functions. You have Most of you definitely have seen this before in the algebra class and or in the pre-calc. We need to recap this really quick so that you can find or rather use this to find the derivatives. Okay. So whenever you have e to the ln x, you can actually write x instead of that. The values are equal. That means if you see anywhere that has written e to the ln x or e to the natural logarithm of x, instead of writing this uh, complicated, seemingly complicated function, you can straight away write a solo x for that, or vice versa. If you somehow need to modify it with exponential function or the logarithmic function, you can straight away for any x, you can rewrite it as e to the ln x or e to the natural logarithm of x. So these values are actually equal. Okay, you can write one for in place. You can write one of these in place of the other. Okay, and if you see natural logarithm of e to the x, you can still write x for it. That means whenever you see e to the natural logarithm of x or natural logarithm of e to the x, you can straight away write x in place of that. Or vice versa, as I said, because maybe in some problems you'll need to rewrite a solo x with the help of the logarithmic function or the exponential function. So you can do uh, either way as per your requirements. Okay, but it actually gives you ample freedom because you will see that we use this property to simplify some problems. Okay, and again you need to remember it. That's the sad part. uh, you'll not be uh, permitted to have this in front of you. Rather, you'll need to remember it. Okay, and that's quite straightforward. Whenever you have exponential with natural log or uh, or the other way, it actually leaves you uh, with the associated function, associated part of it, nothing else. If you have y here, we would have written y. Since it's x, we have written x. Whatever we have here associated with this or this, we can straight away replace that with that particular variable. Okay. What's the next one? This is one of the most important uh, property of I would say natural logarithm. Now we have been using it already in algebra class because I just finished teaching uh, algebra this spring, and we have used this several times there. And I really hope and believe that you have seen this as well, that if you have y equals natural logarithm of x, you can actually rewrite it as this single variable, whatever you have here, equals to e to the this. So this is actually true for any function, or I would say any equation of this format. Any equation of this format. Okay, let me show you um, one example of it. And I would like to have you, uh, I'd like to have, uh, I'd like to tell you to have the slides open so that you can keep an eye on what I'm doing. Okay. Today is 11. And our law says whenever we have y equals natural log of something, let's say x, you can rewrite it as this guy here, x, equals to e to the this. Okay, oh, sorry, I should use this arrow. E to the this. And it actually works both ways. That means whenever you have this format, you can write this one, or whenever you have this format, you can write this one. It actually works both ways. This sign here means it works both ways. That means if you have either one, you can replace it with the other. And let me show how does it work. Let's say you have natural log of x equals to 3. Okay, let's just say. And we're trying to solve it, by the way. Just for example, let's assume that we're trying to solve it for x. That means we're trying to isolate it for, or rather we want to isolate the x. So we know that using this property will leave us with this solo x, which we want. So using that property, we can write this solo x. And as I said, whatever you have on the other side, just take e to the that. That's it. That's your answer. Okay. And we can use this property, as I said, to simplify our life. And you'll soon see examples of it. Any questions so far? We are not doing any calculus as yet, just trying to recap really quick the properties of logarithmic and exponential functions. No questions at all? Okay. Let's go for the next one then. The next property says b to the x for b greater than 0, that means b has to be positive. If you have b to the x equals to so if you have b to the x, can you imagine rewriting it anyway using the first property? Remember, the first property was e to the natural log of x equals to x. So if you have b to the x, can you imagine any way to rewrite this with the help of both exponential and natural logarithm functions using the first property? Don't look at the slide. Try to use the first property. Anyone?
Could you not do anything in this case because you don't have a natural log surrounding that x?
What if you can compare it with this? Let's imagine this is my solo x, although it's not. But let's imagine and consider uh, this as x might lead us to the um, exponential part of it, if we can consider it properly. Okay, so if you can consider this as the solo x, what happens? You can rewrite this, whatever you have, this thing as e to the natural log of this, right? Because if you had x, you could have written e to the natural log of x. If you have this, you can write e to the natural log of this. Do you agree? So many arrows. Let me remove some of those. You can write this. Just imagine this b to the x in place of the x. You can use the same property and write it like this, e to the natural log of b to the x. Do you agree? And we're going to use another property of logarithm to simplify this. So we know if you have natural log of x to the n, you can rewrite the exponent in front and write like this. The exponent comes in front. This is one of the basic properties of logarithm, right? And you have definitely seen it in the algebra class. If you can't remember, no worries. You can refresh your memory now. This is the property, okay? And now if we use this property, can you see what should you get? Don't look at the slide now. Try to use your intuition.
E to the power of x natural log of b.
Exactly. So again, just for a fraction of a second, just imagine this part only, okay? Don't look at the E in the first place. Just have it here and try to eyeball the part in green only, okay? So if we use that property, this exponent will come down, right? Come in front. It will be x, and then the other part, natural log of b. I'm just using this property here. Do you agree? Any question from this? Again, this is not calculus. We're still working on some of the properties of logarithms and exponentials. Okay, now we want to learn some basic derivatives. I mean, the formula of derivatives from this part. Previously, we have seen the derivatives of the trigonometric functions, sine, cosine, tangents, and all that. We have seen the power rule. We have seen the product rule, the quotient rule, right? The chain rule, of course. And now we want to see what happens if we have a logarithmic function, if we have an exponential function, okay? And the formula is whenever you have natural log, the derivative is 1 over x. If you have natural logarithm of x, it will give you 1 over x. Obviously, in terms of x, right? The derivative has to be with respect to x. And this x is always greater than 0. You might be wondering why. If you plug in any value less or even equal to 0 in your calculator, you will see it doesn't give you any value. That means for a logarithmic function, your x or whatever you're taking here, your value has to be strictly greater than 0. The logarithmic functions are actually defined this way. Okay, you can't have any negative values for the logarithmic function, not even 0. It has to be non-negative. Okay, so it's actually for x greater than 0. Okay, now what if I have an absolute value of x? So the thing is, now you can take any value of x, since this absolute value will make it positive, right? This absolute value has the power of making anything, any whatever you input, it makes anything positive. If you imagine a machine, uh, let's say the name of this machine is absolute value. So if you input anything in return, it gives you positive. It always gives you positive. That's the beauty of absolute value. So again, it would be 1 over x But since you can take any value here which will be positive anyway, apart from 0 again, because um, if you input 0, it will still be 0. And as I said, log cannot give you any value for values less or equal to 0. For this absolute value, your x can be negative now because this absolute value will make it positive, but it can't help you with 0 because this absolute value of 0 will still be 0 and natural log of 0 is not defined. We don't have a defined value for that. So the only value which is not possible here is x not equals to 0. Other than that, any value uh, can be taken for this. It's a definition, by the way. You'll see examples of it. Okay. Now, I want to use the chain rule and show you a smallish problem, and then I'll give you a chance to ask questions. Okay. So let's say I have natural log of g of x. Okay. Let's say I have any function of x. It could be anything. It doesn't need to be a solo x like this. So if I can use the chain rule, can you imagine what might happen? Anyone? Use the chain rule. So let's do it this way. So for natural log of anything, what's the derivative? Excuse me.
Would it be
I
1
know
over
it.
g of x times g prime of x?
And why?
Because the natural log of anything is 1 over that value, and then you multiply it by the derivative of g of x.
Exactly. So the natural logarithm of anything, the derivative of that actually is 1 over that, right? Excuse me. Whatever you have with the natural log, the derivative will always be 1 over that. So we can write 1 over this, 1 over g of x. But if you remember, using the chain rule, we know since it's not that solo x, which is known to us, because the formula was for a solo x, for a single x, right? It was for a single variable x. Instead, now we're taking another function. We don't even know what it is. It could be anything. Whatever we have in place of that x, if you remember using the chain rule, we know we need to multiply the derivative of that. We're just using the chain rule, right? Do you agree? Now take your time and see if you have any question. We'll be using this chain rule, as I said, the most number of times in this smallish semester. You can see how can we use this chain rule even with these logarithmic functions, right? It can be used it can be used anywhere whenever you see that for that known part of the function you have another input, you can use the chain rule and simplify your life. Let me show one example. Hopefully it will make more sense. And then I'll give you a chance to ask questions, or rather give you a practice problem which you can uh, do individually. So say you have natural log of x squared, okay? Not x squared, I think I should give you. It's a natural log of 2x, okay? So I know for that, let me have it here again. I know that the derivative of natural log of x is 1 over x, okay? So let's imagine, using the chain rule, let's imagine this is my x. So that means natural log of this, the derivative of this will be 1 over this, right? Whatever you have with the natural log, oops, you'll just take 1 over that. It will be 1 over 2x. But it's not exactly x, which is known to us. It's something else. So whatever it is, we need to multiply the derivative of that. Do you agree? And what's the derivative of 2x? Anyone?
2.
2, exactly. And you can cancel this, and you can see we get a simplified version of it. This is your answer. So the main idea is, again, to use the chain rule whenever you have any other functions like this instead of that x. Use the same formula, have 1 over that, and if it's something else other than that isolated x, then just multiply the product, or sorry, the derivative of that. That's it. Any question from this? No questions at all? Okay, let me give you a practice problem, and then we'll go for the next couple of formulas. We have a couple of other formulas today. And your problem is find the derivative of natural log of sine e to the x. It looks really nice, isn't it? Doesn't it, I should say. So I want you guys to work on this individually, okay? Don't consult it now. Try to use your own concept here. Have the formula in front of you. If you want, you can see the problem I've just showed, okay? And I'll give you 2 minutes for it. Just write it in the chat privately to me once you're done. And then we'll solve it and cross-check our concepts, okay? Your time starts now. So first of all, we want to use the derivative of the known formula for the derivative of natural log of x, and whatever we have with this logarithm, we just take 1 over that, right? So 1 over sine e to the x, and then we need to multiply the derivative of this part because it's not exactly x. We need to multiply the derivative of this, right? Okay. Now, what's the derivative of sine something? What's the derivative of sine something?
Cosine of whatever function that is.
Exactly, very good. So whatever we have with sine, we just need to, sorry, should have used this arrow before. This is here. And for sine, we just write cosine of that, right? And this is here. Okay. But it's not exactly x again. So we need to multiply the derivative of this part. And we know the derivative of e to the x is e to the x, right? So you can rewrite it as 1 over sine e to the x times cosine e to the x times e to the x. You can always simplify it because we know cosine function over sine function is cotangent, right? So you can rewrite it like this. Cotangent of e to the x. Oh, sorry, I don't need this fractions anyway. Cotangent of e to the x times e to the x. Or even to make it more convenient to observe it better, start with e to the x times cotangent of e to the x. Okay, now let's see how many of you have got it right. I can see 1, 2, 3, 4. 4 of you have got it right. Very good. Since we are just starting it, um, that's a pretty good conversion rate. Out of 6, I guess. Yeah, out of 6, 4 of you got it right. So that's pretty good. But if you are not trying it, then I think you'll have only yourself to blame. You should practice a lot of these problems, from this, especially using chain rule, because if you are not getting it how to do this, then you will be in trouble. I'm not going to demoralize you, but I think if you don't practice enough, you'll find it hard. So my suggestion for you, a quick and short suggestion would be to practice at least 5 to 10 problems, and start with easier ones, and then gradually go for more complicated ones. Obviously, which looks complicated. You don't know which problem will be more complicated just by eyeballing. Some problems look complicated, but when you will solve it, you'll see that that one is actually straightforward, which might not be the case always. So start with some smallish and easier problems, and then try some more complicated ones. And once you start getting how things are actually done, you will find it really interesting, right? Any question from this?
I had a question actually. So I know cosine over sine equals cotangent.
Mhm.
But if we didn't go to that full extent of the length and follow that line of what is correct, we left it as cosine over sine, would that be considered wrong?
No, not at all.
Okay.
I'm not sure about my MATLAB because uh, that's an online platform. You can clearly imagine. But if I'm grading it, definitely you will get full credit. No doubts on that.
Okay.
And of course, for the homework, if you somehow see, and if you feel that your work is right, and my MATLAB has actually given you a 0 just because you didn't simplify, just let me know, okay? I'll check your work, and if you have done it right, I'll give you credits on that. Let me know. Because it's an online platform, and it often behaves really, uh, really, really awkwardly, I would say. So if you feel that your work is right and you're not given credit by my MATLAB, just let me know. All right, let's go to the next problem. And our next formula is this. If you have any um, value, let's say 2, 3, 11, any value, any numerical value, and that is actually um, greater than 0 and not 1. That means if you take any value a, which is greater than 0 and it's not 1, if you can verify these two things, whenever you get a function of this format, the derivative of that will be okay. Whenever you have a function of this format, a to the x, where a is a value, numerical value, even if it's not numerical value, if it's written that it's greater than 0 and it's not 1, the derivative of this will be that particular function itself times natural log of this guy, this base. Okay, let's see one example of it. Let's take the derivative of 3 to the x. Do you agree that it satisfies these two conditions? It's definitely, this 3 is definitely greater than 1, and it's definitely not 1. This 3 is greater than 0, and it's definitely not 1, right? It's a 3. So if that's the case, using this formula above, we can say the derivative would be 3 to the x natural log of 3. This is my a. See how easy it is once you know the formula? And obviously, the other side of the coin is if you somehow you know, mess up with the formula, if you mix with another one, then you are in trouble, right? That's the beauty of this uh, derivatives and all that. There are so many formula which is here to make your life easy, but if you somehow mix it with another one, then it actually makes your life even more complicated. All right, any question from this? No questions at all?
Just to understand, this only works because you have a constant as your base to the power of x, and that constant meets these conditions up above, right?
Right, yeah. You're
Okay.
right. All right. So again, I'll give you a practice problem, a really easy one. Let's try this. d dx of okay, yeah, let's try this one. And I'll give you 1 minute for it. What would be the derivative of 5 to the x? Anyone?
It would be 5 to the power x natural log of 5.
Exactly. Again, this base is greater than 0 and it's definitely not 1. So you can straight away say, hey, the derivative will be same function times natural log of 5. Do you agree? Is there anyone who is still confused about it? Okay, so now let's take a break. And after we meet, or rather after the break, when we'll meet, uh, we'll go for the next um, couple of formulas, okay? And we'll start discussing 3.10, which will be the last uh, topic for the exam on Tuesday. All right. Okay, so let's meet at 10:06. Do you have any question from the discussion we had so far? This week or this weekend, I would say, we'll be doing a lot of derivatives. Okay, the homework problems will have these uh, functions uh, where you will be required to use this formula um, and find the derivatives. Okay. All right. So let's go to the next um, pair of formula, and this is theorem 3.18, the derivative of this format, log x base b. So far, we have seen the log with base e. That's why, sorry, I shouldn't write ln of e. It's actually log of e. Whenever the base of the logarithm is e, we have a spatial notation for it, that is ln or ln of x. But we want to see what will happen if the base is not e anymore. Now let's say the base is b, and this base b again could be anything greater than 0, not 1, other than 1. If it's greater than 0 and it's anything other than 1, then for any function of this format, the derivative of this, let me write ddx, derivative of this will be 1 over x, sorry, 1 over x times natural log of b. You might be wondering, hold on a second, how does it even make sense, right? So if you can use the property of logarithms, you can actually simplify this, or rather make modifications and reach this um, result. Let's see how can you do that. Excuse me. So let's try with one example, and hopefully it will make more sense, right? Or should we go for the formula itself? Okay, so okay, yeah, let's try one example of it, and then we'll come back to it. Okay. For now, let's just remember this. We'll need this. Okay. All right. So let's say I'm giving you a function y equals x to the x. What should we do? Anyone? Can you imagine anything?
Isn't that wouldn't that be like an exponential growth then?
Um,
In a sense, because it's x to the power of x, so depending on what your x is, you're exponentially growing.
yeah, I agree, but to find the derivative, now which formula should I use?
Could you use the power rule in this case just to keep it simple, or no?
Yeah, good guess. Um, we can use the power rule to simplify it. But if you remember, the power rule is only applicable um, when the exponent, if you remember, was, I mean, when the function was of this format. That means this was actually a numerical value, or at least not a variable, that's for sure, right?
Yeah, that I was confused. I didn't think that would work, but I just wanted to check and ask.
Yeah, of course. Very good guess anyway. So it's a variable itself. The base is of course a variable. The exponent is also a variable. So we can't really use the power rule. We can't really use the this formula, e to the x either, because it's not e, right? That's a real big problem, isn't it? So that's when our idea of logarithms will come handy. Let's do that. Okay, so if you have this type of problems, the first thing you need to do is to take natural log on both sides. I'll explain why. Okay, let's just trust me now and take natural log on both sides. Okay, whatever I do, I have to do it on both sides. So if I take a natural log on my left, or rather, since it's an exponential, since it's an exponent, um, using the natural log of this format, x to the n, the exponent comes in front. I want to use this property so that the exponent can come down here, which will make my life easier. So that's why I want a natural log on my right. Since I'm taking it on my right, I need to take it on my left as well. Because of this equation sign, I mean equal sign, to keep the value intact, I need to operate same things on both sides, right? Okay, now I can rewrite it as x natural log of x using this property. Do you agree? This is x, by the way. I apologize for my bad handwriting. Do you agree that I can rewrite this as this? Is there anyone who is still confused or who has uh, arguments over this? No questions at all? Okay, now let's see what else can we do. Okay, so let me rewrite that here again so that you can see from where I'm going to the next step. Okay, I'm just rewriting the same line. Okay, now I want to find, remember, I want to find the derivative, right? The derivative of this particular y in terms of x. So obviously, I need to find the derivative on both sides now because we have functions on both sides. So what's the derivative of natural log of y in terms of x? I mean, if I do this, let me rewrite it for you without saying natural log of x. Okay. So what's the derivative of this natural log of y? Can you imagine?
Is it 1 over y?
Almost. Anything else with that maybe?
1 over the log of y?
Not really.
Sorry.
No, you're good as long as you're trying. Your previous guess was actually better.
Would it be 1 over y, natural log of y?
Slightly more. Anyone else? Slightly more modification to that.
Is it times the derivative of natural log of y?
Exactly. It's the derivative, not the natural log of y. Only for y. It's the derivative of y. That means I know for the derivative of natural log of x is 1 over x. So natural log of y will give me 1 over y. But it's not exactly that x. So we need to multiply. I think I should write this format. Multiply the derivative of y. That's it. Again, as I said, using the chain rule is often tricky. It's fun when you are doing it right. So whatever you have in place of that x, you need to multiply the derivative of that. So the derivative of y. Does it make sense now? Do you agree with this?
Yeah, that makes a lot more sense actually.
Yeah. So this is really good that you're trying. As long as you will try, you will see that things will get better because you will try and you will see error. You will try to find the reason behind that error, and then you will actually implement the laws better. Okay. So our left hand side is done. Now let's do the right hand side. What should you do now? On our right. Anyone? What's the first thing comes into your mind when you just eyeball the right hand side, by the way, now? Just eyeball the right hand side. When you see something like this, x times another function or two functions multiplied with each other, what's the first thing comes into your mind?
The chain rule? No, this would be the product rule, wouldn't it?
Product rule, exactly. Very good. It is a product of these two, right? So you can use the product rule. So let's keep x. What's the derivative of natural log of x? If you remember, for the product rule, we keep one function, find the derivative of the other, and we keep doing it for the other part.
It would be the derivative of the natural log of x would be 1 over x.
Very good. Now we'll keep natural log of x. What's the derivative of x? The derivative of x? Anyone?
1.
1. Very good. Okay. So we are done with the derivative part, okay? So on our left, we have 1 over y dy dx. On our left, we have 1 plus natural log of x. Do you agree? I've just simplified it, nothing else. This x and x gets cancelled. And of course, we have natural log of x here because multiplied by 1, in return, it gives me the same thing. Slight simplification. The question now is, are we done? If not, what's the next thing we need to do?
We need to get d of y over d of x alone. We have to isolate it.
Very good. We are looking for the dy dx. We're looking for the value of dy dx. So we want to somehow or other, we want to isolate this dy dx. That means we want to get rid of anything else associated with this. So that means we want to get rid of this 1 over y. Now what should we do?
Multiply both sides by y over 1.
Excellent. So since it's a fraction, if we multiply both sides by y, this will help us to get rid of that, right? So if we multiply both sides by y on our left, that y and 1 over y will get cancelled. We'll have dy dx. And here we'll have y times 1 plus natural log of x. Do you agree? And we know the value of y. Can you tell me the value of y? Anyone?
It exists at the top. If you scroll up, you can see that y is equal to, where was it? It's x to the power of x.
Very good. So we'll just replace it by x to the x. And that's it. That's our answer. That is our answer. See how many things we have done for a single problem. We have used the product rule, chain rule. We have used the formula for the natural logarithms. And so many things for a single problem. But again, if you can do it properly, you'll find it really, really interesting. Any question from this? No questions at all? Okay. Now, should I give you a problem like this or should I go for the next formula? I'll take your suggestions. I'm more than happy to do either way. Do you want a problem to practice now? Or if you want, you can practice once we're done with the discussion. Okay, so since you have no suggestions, I'll go for the next formula. Okay, and we'll start with the formula of the inverse trigonometric functions. Okay, and this time the derivatives will not be straightforward as it was for the general trigonometric functions. Okay, so let me write the formula for you and then we'll practice one or two from each. So the first formula is the derivative of sine inverse x, or one might say arc sine. Some mathematicians say arc sine, some say inverse sine, some say sine inverse, whichever you feel like saying, okay? Whichever you are comfortable with. Okay, so the derivative of it is 1 over 1 minus square root of 1 minus x squared. Okay. All right. Now, if you are given, let's say, a function like this, let me show one problem. Derivative of sine inverse, let's say 5x. Can you imagine what could be the derivative of it? Anyone?
Would it be 1 over the square root of 1 minus 5x squared?
1 over 1 minus 5x squared. Okay, yeah, this part is done. This part is right. So 1 over square root of 1 minus 5x squared. Yeah, you're right. Because in place of x, we have this 5x. So we take the square of this 5x. But are we done? Is there anything we should do to complete this solution?
Do we need to rationalize it?
Not really. What else can we do? Or do you think it's done? If you think it's done, then it's fine. But if it's not, what else we need to do? Anyone? The first question is it the x we know? We know the formula is for x. Is it the x? Is it that isolated variable? Or do we have anything else with that? Excuse me. Is it of the same format?
Would we have to use the chain rule?
And how do you think we should do that?
Just multiply everything there by the derivative of 5x.
Very good. We need to multiply the derivative of 5x. Yep, because it's not x, it's 5x. Whatever we have in place of the known format, we know the format for x only. We don't have that x here. We have something more. If we have whatever it is, if we have anything else other than that particular x, that particular format, whatever we have, the chain rule says you need to multiply the derivative of that, right? So what's the derivative of 5x?
5.
Very good. So our final answer should be 5 over 1 minus, I think I should write 25 x squared here. And that should be our answer. Any question from this? Any question? No questions at all? Okay, let's move to the next one. And if you can open the slide for me. The slide is, yeah, 3.10, slide 8, my bad, sorry. Slide 8, 3.10. We have the formulas here, all the formulas, okay? You can see, let me share the screen. And then I'll give you a problem to practice. Put something in the chat. I can't see the chat, what happened, but I can see there is something in the chat. But when I'm trying to open it, it's not opening. I wonder why. Anyway, let's check it later. All right, so this is the slide I was talking about. You can see the derivatives of the inverse trigonometric functions are slightly more complicated. Okay, slightly, not really. And again, it's really easy to mix one with another. So I'd suggest you to practice a couple of problems so that you can use it properly. Okay. And now I'll give you, show you one or two problems, and then I'll give you time to practice a couple of more. Okay. So let's try one of the formulas which we'll use probably the most times, the formula for the arctangent. The derivative of tan inverse of x is 1 over x, 1 over 1 plus x squared. This is the formula. And we'll probably use it for the most number of times. Okay. All right, let me show you one example of it, and then I'll give you one or two problems. All right. What if I say I have to find the derivative of arctangent of x over y. Let's try this one. So now I'll just follow your instruction. One by one, you will say, what should I do and why? I mean, what's the reason behind that? And I'll just copy your work, okay? Now, who wants to tell me what's the first thing comes into your mind when you see this problem? What should you do? It's not easy, I'm telling you.
Well, we want to set it up. We want to set up arctangent as the derivative of that, right? So you'd have dx or d over dx tangent to the -1, y over x equals 1 over 1 plus y over x squared.
Why do you have ddx on the right side?
Well, you're taking the derivative you want the derivative of x. It should be oh, is this on the right side? Sorry, my bad. It shouldn't be on the right side, it should be on the left side.
I already have the ddx, yeah, so I don't need any more ddx. on my right, I just need to write the derivative here on this place. I know the formula.
Are you showing us the problem? Because at least what I'm seeing is derivatives of inverse trigonometric functions on the screen right now.
Oh, I forget. Sorry, I forgot. Sorry. I was actually writing in my iPad. Ah, that's really bad. Thank you for reminding me. My bad. Okay, so let's do that again. That's the difficulty of showing more than one things simultaneously. Okay, so yeah. Here is the problem I was talking about. What's the first thing when you see a problem like this? What's the first thing comes into mind? It's tan inverse x over y.
Are we going to be using the product rule?
I can't see any product. I can't see any functions multiplied with each other. Anyone else?
Well, then wouldn't we do what David said by plugging in x over y for x squared? So it'd be 1 over 1 plus x over y squared.
Like this?
Yeah.
Okay, are we done?
No.
Okay, what else we need to do?
Do we need to multiply by the derivative
Derivative of what? Very good. Yeah, derivative of what?
of x over y?
Of x over y. Very good.
Okay.
Okay. Okay, so let's simplify this first term. So this will be 1 over 1 plus x squared over y squared. Now what's the derivative of x over y? This would be interesting.
Is it 1?
Nope, it's not 1. If it was only x, then it would have been 1. We have x over y. Anyone else?
Now, at this point, we have to simplify this fraction because you can't have a fraction over a fraction, right? So wouldn't you, you basically have to flip the fraction in a way, right? So you have to flip x squared over y squared so that y squared rests above the main fraction in the numerator, right?
No, I'm talking about the derivative of x over y. What's the derivative of x over y? Yeah, we'll go to the simplification part of this. But right now, we're trying to find the other half of the problem. What's the derivative of x over y? Can you imagine anything? What does your intuition say? Which formula can you use? Can you think of out of your head?
Would we have to use the quotient?
Very good. Yeah, we have to use the quotient rule. So we know the quotient rule says the denominator squared, keep the denominator, find the derivative of the numerator, minus keep the numerator, find the derivative of the denominator. Do you agree? I've just used the formula, nothing else. Keep the denominator, find the derivative of the numerator, and then subtract, keep the numerator and find the derivative of the denominator. Do you agree? All right.
Yes, and that would simplify to
Yeah,
y times 1, right? Minus x times the derivative of y over y squared.
exactly. Yeah, definitely.
Okay.
Mhm. Okay, now let's simplify the first half, which is this. So for this, I can rewrite it as y squared plus x squared over y squared. Do you agree? Or do you want me to explain how did I do that? You have already seen this in algebra class, that's for sure. But if you want me to re-explain, I'm more than happy to do that. Just go for the, try to convert it uh, to the same denominator. If you can, if you have same denominator for these two terms, you can actually add the numerator, and that's what I have done. So I have 1 plus x squared over y squared. I want to have y squared for this first term in the denominator. So what I'm doing is I'm multiplying and dividing by y squared, because in return it actually gives me 1, right? I can do that. So now, since I have the same denominator, I can just add the numerators. Okay. And if I simplify the second half, obviously the derivative of x will be 1, and the derivative of y would be dy dx over y squared. If I simplify it more, sorry, this y squared can be flipped to here, can be taken to here, y squared plus x squared. And again, if you're wondering how did I do that, this was 1 over y squared plus x squared over y squared, which is literally dividing this, right? I was just dividing this particular function, or rather, uh, 1 was divided by this, right? So I can rewrite it as 1 over this. You can always flip this one when you change the sign. And this is what we have here. Okay. And now, if I rewrite the second half, x times dy dx over y squared. So this y squared will get cancelled. So we'll have y minus x dy dx y squared plus x squared. This is my answer, because we are looking for the derivative of tan inverse of x over y, and this is my answer. Any question from this one? I hope you have some questions.
Would you be able to cancel out a y on top and bottom in this case?
Good question. Good question. And the answer is no, because if you want to cancel out something, you need to have that particular thing factored out, right? You can't really factor out y from the numerator, neither from the denominator, because in the second term there is no y for each cases. There is no y term in the second term, I mean in this term and in this term, which can be factored out.
Oh,
Factor
okay.
out, then you can cancel out y.
Okay.
Any other questions? Anyone? Do you feel that it's really, really complicated, or do you think it's doable? Let me see if there is anything in the chat. I can't really open the chat, and I don't know why. I was able to see it before the break. There could be some technical issues anyway. All right. Any question from this? Again, take your time, okay? This is a complicated problem, no doubts on that. If you try one or two of these problems, you'll see that there are so many things to be done here, so many things to keep in mind. Definitely it's doable, but not before you actually practice some and gain some experience how to do these problems. Okay, let's go for the next one. Okay, the next one is, yeah, let me give you a problem. I think we have enough time, because if you don't practice, I don't think things will be clear to you. So let me give you a problem. Let's say ddx sine okay, sine inverse of e to the x. Yeah, let's not complicate it too much. Yeah, so do it for me, and again I'll create breakout rooms for you. 4, 3, 3. Really? We're 12 in total? Okay. Or 11, in fact. Okay. All right. So your time starts now. Okay. So, from each of the groups, can anyone tell me, were you able to solve it? Is there any group which couldn't solve it at all? Or if you think that you didn't do it right, you haven't, or you have made a mistake somewhere, you feel like that? All the groups have done it properly?
Well, we hope we've done it properly, certainly.
Yeah, that's what I want. If you feel that it's done properly, that's what I want in the first place, because if you're not confident enough, then we need to practice more, right? We need to solve more problems. Okay, so what's the derivative of sine inverse e to the x? What's the first thing we need to do? Anyone from the first group? What should you do? Not from the first group. If you want to share your work, you are more than welcome to do that.
What my group did is we just wrote 1 over the square root of 1 minus e to the x squared.
Like this?
Yes, and then multiplied it by the inverse of e to x, which is just e to the x.
The inverse of e to the x?
Or derivative.
Oh, very good. Yeah, very good. Yeah. So yeah, your answer is absolutely right. So it's 1 minus e to the x. You can instead write, let me remove this first. Instead, you can write e to the 2x, right? Times e to the x. Okay, so that's your answer for this problem.
Would you not, would it not be e to the x divided by the square root of 1 minus e to the 2x?
I didn't understand. Would you please repeat it?
So would you not just multiply that e to the x across the top so that it's e to the x divided by, yeah, like that, divided by the square?
It's actually the same thing.
Okay.
No worries. Yeah. Okay. Any other questions? So up to this will be in your exam. Up to this 3.10. So I'll add one more video, at least one more, hopefully two. At least one more video tomorrow with some really uh, essential yet tricky problems, worked out problems. I'll show some problems which will be helpful for you guys in the exam or even in the homeworks. But yeah, the exam will be from 3.1 to 3.10. Oh, sorry. Again, I'll keep the exam really simple.